Okay, another circular motion problem that you might encounter is something similar to what is known as the Gravitron ride. I'm not sure if you've been to the state fair or any other smaller scale amusement type park, but basically what this ride does is it spins around in a circle, and it actually tilts also at an angle. But we're just going to talk about it spinning at a perfect circle. There's someone in the center that operates the apparatus, so here he is, and then there's usually kids around the side laying on these little platforms that can move up and down. So if you want to see exactly what this, how it affects the people inside, you can go ahead and click on this link below. It'll be in the comment section. It's another YouTube video to watch what this ride actually does. Basically, the kids go up and down depending on the angle at which they're at. When it's perfectly a horizontal spinning circle, they're all up at the very top. It's similar, how you feel when you're in this ride is similar to if your car makes like a sharp turn and you feel like you're being pushed towards the whichever, opposite of whichever way you're turning. Okay, so here's an example. This is just a picture of how we might draw the free body diagram. So here's someone on the side. Here's the operator in the center. The forces acting on the person on the side is force due to gravity down. The normal force from the wall pushing the person towards the center. And then the force of friction. So the force of friction between the wall and the person is what is keeping them from falling. And the normal force is considered the centripetal force, keeping the person moving in a circle. So let's say we know that the radius of this ride is 5 meters, and we are looking for the minimum coefficient of friction in order for someone to stick to the wall and not fall. The time for one revolution is 2 seconds, and like I said, the Gravitron has a radius of 5 meters. So we already drew our free body diagram. The next step would be to sum up our forces, both this time in the X and Y direction. We could also find the velocity of the ride. So the velocity is equal to the distance divided by time. Since we know that it takes 2 seconds for the Gravitron to make one full turn, we could solve for velocity. So 2 pi r over t, time. 2 pi times our radius of 5 divided by 2 seconds gives us 15.7 meters per second. So that part is going to be necessary to solve for our forces. So now that we did that, we can sum up our forces in the x direction. So the only force acting in the x direction is the normal force, and this is the centripetal force. So it equals mass times acceleration centripetal. If we go ahead and substitute our equation we know for acceleration centripetal, v squared over r in. And our forces in the y direction, since the person isn't accelerating up or down on the wall, the force due to friction is going to equal the force due to gravity. There is no acceleration in the y direction. And we could do some substitution here. We know that the force of friction is equal to mu, the coefficient, times the normal force. So we see two equations here. F normal, and we see another equation with F normal. So if we solve for coefficient first, we get mu equals Fg over Fn. And let's go ahead and plug this other Fn right here in for this Fn, so we'll get rid of a normal force. We're left with mass times gravity divided by mv squared over r. So we have a fraction divided by a fraction, so what I did is I just multiplied by the reciprocal. So mg divided by mv squared over r is the same thing as mg times r over mv squared. You'll notice the masses cancel, leaving us with g r over v squared. Plug in our givens, 9.8, 5, and 15.7 meters per second. Plug it into your calculator, you should get a coefficient of 0.199.